Hey everyone, welcome back to LabCoatz. So, a few months ago, I was poking around on Amazon when I came across this seemingly innocent listing for pineapple fragrance. To the average person, this probably seems like nothing special. Maybe an interesting gimmick for soap or candle makers, but that's about it. However, to a chemist, this is actually a pretty decent steal. You see, according to the listing, this bottle of perfume is actually 100 milliliters of reasonably pure allyl cyclohexylpropionate, a compound that not only smells good, but can also be broken down into allyl alcohol with relative ease. This actually makes it fairly useful to me, since the alcohol can be further reacted with hydrobromic acid to form allyl bromide, a useful alkylating agent that I'll be needing for an upcoming project. Now, there are other ways to get allyl alcohol, of course. Distilling glycerin with formic acid at high temperatures is certainly a viable route, but the reagent costs are usually higher, and the yields are somewhat lower. It's also possible to simply purchase allyl alcohol, but sellers are usually few and far between. I only found one listing on eBay from an overseas seller, and it was somewhat overpriced with the shipping included. On the other hand, hydrolyzing an allyl ester like this has the potential to be over 90% efficient, and the only other ingredients needed are sodium hydroxide and water. This makes the process attractively cheap, which, being honest, is a major factor when it comes to home chemistry. Plus, the leftover carboxylic acid can be recovered and used in other projects, as I'll show in a future video. For this synthesis, I utilize the following reagents: sodium hydroxide, hydrobromic acid, sulfuric acid, and allyl cyclohexylpropionate. The ethylene glycol seen here is optional, but it can be added to break the azeotrope allyl alcohol forms with water during redistillation. I actually tried using ethylene glycol as the solvent for this reaction at one point, but the sodium hydroxide had trouble dissolving, so I ended up adding water anyway, which did dilute the allyl alcohol that distilled over. It might be possible to run this reaction with nothing more than sodium hydroxide and the ester, but I was too worried about things overheating and caking up to try. To start things off, a 500 milliliter boiling flask was filled about halfway with water, and 20 grams of sodium hydroxide was added and dissolved. In reality, I probably could have used half this much water, but I wanted to make sure everything remained dissolved during the distillation. Once the hydroxide solution was prepared, I dumped the whole 100 milliliter bottle of allyl cyclohexylpropionate into the flask, which seemed to dissolve pretty quickly. If you attempt to replicate this procedure yourself, I honestly wouldn't bank on things reacting this fast. This batch of allyl ester was recovered from that less successful previous run with the ethylene glycol, and it was definitely tainted with some of the more reactive carboxylic acid. The reaction that is occurring here is known as a base-catalyzed ester hydrolysis. Acid-catalyzed hydrolysis is also possible with many esters, but the use of a base like sodium hydroxide comes with one distinct advantage. It will form a non-volatile carboxylate salt instead of a free carboxylic acid. This essentially traps the side product and helps push the reaction to completion. Plus, it really helps minimize the unpleasant odors associated with carboxylic acids. Cyclohexylpropionic acid isn't particularly foul, at least when compared to something like butyric acid, but it does have a somewhat sweaty, feet-like smell that somehow also hints at the original pineapple scent. Not terrible, but also not something you'd enjoy for very long. So, with all the ingredients added, the heat was cranked up and the product was allowed to distill over. As mentioned earlier, allyl alcohol forms an azeotrope with water, which boils at roughly 88 degrees Celsius. To ensure I recovered the most product possible, I collected everything that came over below 98 degrees, since the boiling point will inevitably change with the concentration. Now, during the distillation, I made the mistake of not setting up some kind of bubbler or trap to prevent vapors from escaping, and, as a result, I got to experience the wonderful lacrimatory effects of allyl alcohol, which were unpleasant to say the least. I had to wear a full-face respirator for this whole procedure, because if I took it off for more than a minute, my nose would burn and my eyes would start to water. Also, in spite of what the Wikipedia article says, I didn't find the odor at all mustard-like. It was more musty and mold-like, but with an acrid bite that seemed somewhat unusual for an alcohol. By the end of the distillation, I was left with a few hundred milliliters of cloudy liquid. I'm not really sure where the cloudiness came from in this case, but I'm guessing it was from a small amount of unreacted ester carrying over with the distillate. Whatever it was removed by the second distillation I performed, which left me with 75 milliliters of azeotropic 73% allyl alcohol. I could have redistilled this with ethylene glycol to get a nearly anhydrous product, but since a little water wouldn't hurt subsequent steps, it didn't really seem worth the extra effort. Moving on to the second half of the synthesis, my next task was to convert the allyl alcohol to allyl bromide. To do this, I ended up following a procedure I found on the Organic Synthesis website, which called for a mixture of sulfuric and hydrobromic acid. Now, it might be possible to simply use sodium bromide in excess sulfuric acid, which would form the hydrobromic acid in situ, but I had already messed up a few different reactions that month, and I wasn't in the mood to potentially screw up another. And since I'd be needing the hydrobromic acid anyway for a future project, I just bit the bullet and distilled a small batch, according to Thylab's procedure. Once the acid was prepared, I added the entire 75 milliliter portion of azeotropic allyl alcohol to a 500 milliliter flask. Then, about 120 milliliters of hydrobromic acid was dumped in, followed by 30 milliliters of concentrated sulfuric acid. Although the paper called for the two acids to be mixed first and the alcohol added second, I actually found this to be a pretty bad idea, since it tended to liberate large amounts of hydrogen bromide gas from solution. Not exactly something most people would want to have happen. With all the reagents combined, a condenser was attached for distillation, and a pressure-equalized addition funnel was loaded with another 30 milliliters of sulfuric acid. Once I was ready, I opened the stopcock and allowed the acid to slowly drip in. As this happened, the solution became darker and darker, and almost immediately, distillate began pouring over. Before, I was honestly worried about how well this procedure would work, since my hydrobromic acid was only 42% instead of 48%, and my sulfuric acid was 93%. But as you can probably tell, it all worked out just fine. Almost all of the allyl bromide came over within 5 minutes of adding the second portion of sulfuric acid, but I kept distilling for another hour just to make sure everything reacted. In the end, I came out with about 40 milliliters of crude product. To clean it up, I washed the allyl bromide with 2 separate portions of dilute sodium bicarbonate solution, which should have neutralized any residual hydrobromic acid. Then, to get rid of the cloudiness and remaining water, a few spoonfuls of calcium chloride were added, and the product was mixed until perfectly transparent. The final yield of dry, acid-free allyl bromide was 37 milliliters, which correlates to a yield of roughly 50%. Since the paper mentioned a yield of at least 92%, this is somewhat poor. But, as usual, I have a few excuses. For one, it's possible that my allyl alcohol wasn't nearly as concentrated as I thought, although that doesn't seem very likely since I distilled it twice at its azeotropic temperature. Another possibility is that I didn't use enough hydrobromic acid. The paper called for a somewhat larger molar excess than I used, and my acid was a bit more dilute based on its density. However, the most likely case is that I add the sulfuric acid too fast or with too much heating, which led to the lovely black tar found in the boiling flask. Whatever the case, this is still plenty of allyl bromide for my upcoming projects. Now, at this point in the video, I've come to realize that there are 3 main things I usually do with the end product. Either I smell it, burn it, or on rarer occasions, taste it. So, why break tradition? Naturally, I won't be tasting the allyl bromide, since I value life without cancer and all. But after working with it for a while, I can at least tell you a bit about the smell. It doesn't seem to have the lacrimatory properties of its parent alcohol, but it does retain a lot of its acridness, while also having that sort of gross sweetness typical of halogenated hydrocarbons. Regarding the burn test, allyl bromide is honestly not super flammable, but when it does burn, it lets off a decent amount of soot and white hydrobromic acid vapor. Production of carbonyl bromide, the bromine analog of phosgene, might be possible, but it seems unlikely given the compound's comparative instability. Regardless, if the opportunity ever presents itself, please don't burn allyl bromide. I did this in a well-ventilated area with a certified respirator, and it still probably wasn't a very good idea. Alright, that's pretty much everything I've got for you today. As always, I'd like to thank you all for watching, and encourage you to subscribe for more fun. In my next video, I'll be using the allyl bromide I made to create an ultra-potent caffeine analog, which is rumored to have up to 10 times the strength of regular caffeine, while also having lower impacts on the heart. And yes, after taking several precautions and doing extensive research and testing, I will be trying this stuff on myself, in the form of the world's sketchiest energy drink. Spoiler alert, it definitely worked as advertised. Maybe a little too well. Anyways, at this point, I'd like to give a big shout out to all my supporters on Patreon. Without donations from people like you, I truly wouldn't be where I am today. Remember to like, share, and subscribe, and I'll catch you next time. LabCoatz, out.